Now we take an example, that is example 1 from Kosella and Berger's book, that is page 331. The statement of this example, that is, let x1, x2 up to xn are the IID normal with mean mu and variance sigma square. Then we know that the statistic x bar and s square are unbiased estimated. It is well-defined result. Since expected value of x bar, that is mu, and the expected value of s square, that is sigma square, for all mu and sigma square, this is true without the normality assumptions as well. The MSE of these estimators are, that is the expected value of x bar minus mu whole square, that is the variance of x bar, and which is equal to sigma square over n. That is well-known result, variance of x bar, that is sigma square over n. We use many times this result, and it is well straightforward result. The second one, which is the most important, that is the expected value of capital X square minus sigma square, that is the variance of x square, and this is equal to 2 sigma 4 over n minus 1. So basically we focus on the second result, which is more important, and the first result is very straightforward. So we start from the second result. Suppose the samples are taken from the normal distribution, and we know that we have already shown this one, n minus 1 s square over sigma square is basically distributed as chi square with n minus 1 degree of freedom. We have already shown this one. So we need the variance of this quantity, so we take the variance of both sides. So that is variance of n minus 1 s square over sigma square, that is equal to variance of chi square n minus 1 degree of freedom. So when we apply the variance, basically it becomes n minus 1 square over sigma raised to power 4 into the variance of s square, and that is equal to, and we know that the variance of chi square, which have n minus 1 degree of freedom, that is 2 into n minus 1. So the variance of s square becomes 2 sigma raised to power 4 over n minus 1. Actually, we are interested in the MSE. So the MSE of x bar, the MSE of x bar remains sigma square over n if the normality assumption is dropped, because that is well-defined result. So however, the MSE of s square does not the same. MSE of s square जो है does not remains the same. If the normality assumption is relaxed. So we consider an alternative estimator of sigma square, that is the MLE, and we know that the sigma square, that is 1 over n sum xi minus x bar square, and this is equal to, we know that that is n minus 1 over n s square. So if the sample, it is the sample, to prove that, it is very simple to prove that the expected value of sigma hat square, that is actually the expected value of n minus 1 over n s square, and we know that it is equal to n minus 1 over n sigma square. So sigma hat square is a biased estimator of sigma square, and we can calculate it as, so first the variance of sigma hat square, that is actually the variance of n minus 1 over n s square, and this is equal to, because these are the constant term, n minus 1 square bahar aa jayega, over n square into the variance of s square aa jayega. And we know that we have already find the variance of s square, so just put the result and solve it. We will find the result, that is 2 n minus 1 over n square into sigma raised to power 4. Hence, for MSE, that is basically the expected value of sigma hat square minus sigma square whole square. That is basically the variance plus the bias term. That is the variance here, that is 2 n minus 1 over n raised to power 4 sigma square. Sorry, sigma raised to power, that is 2 n minus 1 this, and that is raised to power sigma 4, sorry, that is sigma 4, plus that is the bias term, which is n minus 1 over n sigma square minus sigma square whole square, and when we evaluate it, that will give the result, that is 2n minus 1 over n square into sigma raised to power 4. Thus, the expected value of sigma hat square minus sigma square whole square, which is equal to 2n minus 1 over n square sigma raised to power 4, is less than 2 sigma raised to power 4 over n minus 1, which is basically the expected value of s square minus sigma square whole square, which shows that the sigma hat square has smaller MSE than s square. And again, this is the trade-off variance for biased. The MSE can be improved by trade-offing between the biases and the variances.